Okay, everybody, I'm really sorry I have been ill this week and haven't been able to teach you, and unfortunately you'll probably know by now that I've realised I'm on a training course this week during our lesson. Don't worry, we will have time to catch up on everything, but I didn't want to leave you hanging with all that work that I set without talking some of it through. So let's see what we would have done in the lesson. Um, We're looking at covalent bonding using dot and cross diagrams, which you've done at GCSE, but we kind of take one step further. We need to be able to describe covalent bonding and to represent it using dot and cross diagrams as well. But also at GCSE, as with a lot of things at GCSE, we used a rule or a model that worked up until then. We used something called the octet rule, and we talked about atoms wanting a full outer shell. And when we talk about electronegativity, which comes next, we'll talk about that more, but it's about certain nuclei or certain atoms having more attraction for the electrons than others, and sometimes they have so much attraction for electrons that you end up with an ionic bond. And sometimes the electron density is shared by two nuclei more equally, in which case we get a covalent bond. So we're going to still talk about the octet rule for now, but I want you to bear in mind that that is just you will have come across some dative covalent bonds by now. And what this is about is when one particular atom donates a pair of electrons. So if an atom has a lone pair, then instead of having to find another atom to share electrons with to make a bond, it donates both the electrons in its lone pair to effectively make the bond itself, and we call this a dative covalent bond. Ammonia is NH3, and nitrogen has used three of its outer bonding electrons to form bonds with covalent bonds with hydrogens, but it still has a lone pair. So when ammonia forms an ammonium ion, when it bonds with a hydrogen ion, it's able to give its lone pair to the hydrogen ion. If you think of what a hydrogen ion is, a hydrogen atom only has one electron in its outer shell. So if it's lost that electron to become a hydrogen ion, then basically it's just a nucleus. So the nitrogen atom can donate the lone pair to the hydrogen, and it can accept both those electrons to make an ammonium ion. So the non-bonding pair can be donated if another atom, ion or molecule is able to accept it. And whereas before we've been drawing covalent bonds just with a line, now we use an arrow to show that there is an atom that supplies both the electrons. So if you look at the textbook, they'll give you another definition to learn. We'll be looking at these in the lesson, so get this in your book. Oh, that's my son in the background pretending to be a dog. Definition of a dative covalent bond is one where a shared pair of electrons has been provided by one of the bonding atoms only. Write that in your book somewhere. Make sure you remember that. Make sure you learn it. Hello, doggy. So we have for the moment got this octet rule, and we'll go with it for now. And so we'll look at some examples that break it. So boron trifluoride is one of the ones that comes up all the time. Boron has 3 electrons in its outer shell. It's quite happy, if you want to talk about this in terms of happiness, it's quite happy to go around as BF3. So that's one example. Sometimes you end up with an atom that has more than 4 electron pairs in it. So if you look at page 57 in the textbook, if you look at SF6, then you've got an example there of sulfur with 12 electron pairs, 12 bonds, 6 bonds. So again, things that break the rule. Now these two are worth learning because they use them as examples. But if you want to pause now and just have a go at trying to draw what happens when BF3 reacts with NH3, and also see if you can draw, there's aluminium trichloride, AlCl3. Now this forms something called a dimer. Okay, so here's the answer. So you've got the boron trifluoride that's able to accept the electron pair from the ammonia, from the nitrogen in the ammonia to form one compound here. And there we've got the dimer of AlCl3. And if you draw out the dot and crosses, you will see that aluminium does end up with 4 electron pairs in its outer shell. Nearly there, but I just wanted to quickly run through the homework that you did. Pause now if you need to go and look for it somewhere, and then we'll go through it. I'm using new software here, so you'll have to bear with me. Well, you can see that would have been hydrogen at the top here. So this would have been hydrogen here, and the hydrogen molecule, we've looked at this in lessons, so I mean, you know that there's 2 hydrogen atoms that are each sharing 1 electron, so there's a dot and cross that's shared between the 2. Here we've got hydrogen chloride. Now again, I say this when I teach it at GCSE, and I'll say it again now. However simple you think something is, please, whenever you draw a dot and cross diagram, go through the process of counting the electrons in the outer shell. Because in general you're looking for 8. There are some that break the rules, but in general we're looking for 1, 2, 3, 4, 5, 6, 7, 8. And again here, ammonia. So here's ammonia that we've been looking at. If we look at the dot and cross diagram, we've got 1, 2, 3, 4, 5, 6, 7, 8 electrons. You must go through this process. Here, hydrogen's got the 2 electrons it's expecting. Carbon has got the 8 electrons it's expecting in its outer shell. So go through the process. This is question 12, by the way. So now, but at the top here, the sulfur has another 2 electrons in its outer shell. So, okay. Whereas here, carbon disulfide, again, we've got the double bond here between the carbon and the sulfur, but that means that the sulfur has 2 lone pairs that are left over. But again, if you count the electrons, 1, 2, 3, 4, 5, 6, 7, 8 in the carbon, 1, 2, 3, 4, 5, 6, 7, 8 in the sulfur. So if you go through the process of counting the electrons, everything is as you would expect it to be. And here, nitrogen with 3 fluorines attached to it. Again, we've got a lone pair, which means that the nitrogen has the 8 electrons, whereas the fluorines all have 8 electrons, and they've bonded once there. This would be a hydrogen atom down here. For question 13, nitrogen has 1 lone pair, oxygen 2 lone pairs. Fluorine, once it's formed a covalent bond, has, if it's used one of its electrons, if you imagine it is, if we've used one of those electrons to form a bond, that means that we're ending up with 6 electrons. That's 3 lone pairs. Number 14, we've got multiple bonds here, but still, even though that carbon has formed a triple bond, it's still got 1, 2, 3, 4, 5, 6, 7, 8 electrons in its outer shell. Now the carbon only originally had 4 electrons in its outer shell. These are the dots, and we've used all of those. So that means to fulfill the requirements for both of them, the oxygen has had to donate 2 electrons to the bond. It's formed a dative covalent bond, as well as the sharing going on here, and that's the bonding there. Now this is nitric acid here, HNO3. Again, what we've got here is quite complex, but the hydrogen, if you go around and count the electrons, hydrogen, 2 electrons in its outer shell as we'd expect, 8 electrons in the oxygen. That's simple, that's just shared. Here we've got a simple sharing, so but we've got a double bond, 2, 4, 6, 8 electrons in the oxygen here. But that means that the nitrogen started off with the crosses here. 1, 2, 3 have been used. It's got another 2 left over. Remember, it has this lone pair quite often, and it's got one here that it's donated to the oxygen, so that the oxygen So it forms a dative covalent bond with the oxygen. So here we've got a dative covalent bond being formed with the hydrogen ion. Here you see it with the dot and crosses. We've got two electrons, the electron pair, the lone pair from the oxygen going with the hydrogen. And here we've got boron trifluoride, which readily reacts with ammonia because the boron atom in BF3 has only 6 electrons in its outer shell. Okay, do email if you have any questions about this, obviously, as usual, and again, apologies, it's just been an awful week, and I'm sorry this is the way that it's fallen.